Good evening, everyone, and welcome to our Tuesday walkthrough where we explore the concepts and the code for the weekly materials. This week, we're going to talk about basic statistics in Python. So let's go. All right, so at this point, we're going to open our first Module 1 Basic Statistics workbook in Google Colab, and we're going to work through it. Here you will learn how to read data into a Python notebook, how to inspect the data, how to conduct an exploratory data analysis, also called an EDA, with basic statistics, and how to build a few basic plots. Let's get started. So the three basic Python libraries that you will need for each and every workbook are NumPy, is the fundamental package for scientific computing, Pandas, which is the Python data analysis library, and Matplotlib, which is a very powerful graphics package. In order to load the libraries into your runtime environment, you will need the import command. So you will type import and then NumPy, which is our first library that we're going to use, as, and then you set an alias for it. That is standard usage. Here, the standard alias for NumPy is NP. For Pandas, the standard alias is PD. And for Matplotlib, specifically PyPlot, which we're going to use in a little bit, the standard alias is PLT. And we're going to use one of these libraries right away, namely the PD Pandas library, in order to read our data file into our runtime environment. The data file that we're using, namely the adult data simplified data file, sits on the instructor's GitHub here. You can see that from the URL. And we are using an encoder, an ISO 8859 encoder, because we want to ensure that all our characters are in ISO standard. We are going to use the pd.readcsv command here in order to load the data set and then assign to it the name adult. And adult will be the name of our data frame. All right, so let's get started. In order to execute a line of code in your Colab notebook, you will need to run the cell, which I just did, and then you will see a little wheel here that turns. And as you're seeing right now, we got an error. And yes, errors are a way of life, and it is important to understand what an error message tells you. And this is the very first really important lesson that I want us to learn, to really read an error message. So let's see what the error message tells us. It says name error, traceback, IPython input in module. So it has something to do with an input. And then it gives us the line of code, adult equals, here we go. This is exactly this line of code. And we can also see that this line of code has caused the error because it has the red undersquiggle. And then we get the actual nature of the error here, the explanation, which is name error. Name PD is not defined. Okay. Why is name PD not defined? That's what we can ask ourselves. Or we can search Stack Overflow. If I click on this button here, as you have seen here, a Stack Overflow search is being opened. And then in this Stack Overflow search, you can find answers to any of the questions that may occur when you see an error in Google Colab. However, before we go that route, let's really think about what this means. Name error, name PD is not defined. Well, have we loaded our libraries? I already showed you how executing a piece of code requires pushing this button here. And in fact, we have not. So let's load our libraries and let's see if that will solve the name PD is not defined error, because here we are in fact defining PD. All right, I'm loading the libraries. As you can see, there's a little green check mark that shows me that the libraries, that the code in this box here has loaded. And now I'm just simply going to rerun this code here. And as you've seen, we have a little check mark here as well, and our error has fixed itself. And that's simply because we have loaded our libraries here. So the next step then is, once we have loaded our data set, we're going to inspect our data. We have a number of options available to us. Our first option is to look at the entire data set. This is the entire adult data frame here. So I'm going to uncomment this here, this line. Comments in Google Colab are the same as comments in Unix. They are prefaced with a hash mark here. So as you're seeing, I'm displaying basically the entire adult data set here. We're seeing we've loaded 32,560 rows into our environment and 12 columns. Now, with a smaller data set, like one with 32,561 rows, that's really not that much of a problem. It does get problematic when you have about 1 million rows in your data set and you're trying to load that into your runtime memory. That may slow things down. And if you just want to look at what the data actually looks like in your data set, well, you have options. One of the options is to use the head command. The head command shows you the first few rows, however many rows you identify in the parentheses here. So if we look at adult.head and we identify 5, we will see the first 5 rows. The opposite of head is, of course, tail. But before we go to tail, let's take a quick look at the indexes here, the indices for these rows. You're seeing that the index starts with what? With 1 or with 0? With 0, right? So 0 is very important because really we need to understand the number of the index if we are trying to count rows later on. That will become very important. So I want you to understand that the indices in Python start with 0. All right, so we're going back to our adult data set here, and we're going to play with adult tail. Now, if head shows us the first part of the data set from the beginning to however many rows we specify here, tail shows us the bottom part of the data set with however many rows we specify in here. So adult.tail and then 7 shows us the 7 last lines of our data set. Now, remember how we said there's 32,561 rows in the data set, but here the last number we're seeing is 32,560? Well, that's because what gave us the first index number of the data set? 0, right? So that's why if we're starting to count at 0, then we end up with 32,560. Now that we've talked about the rows in our data set, let's talk about the columns. You'll see we have columns with numeric values here, like age, education years, hours per week, and income USD, and we have columns with string values such as work class, education, marital status, and so on. Can it be useful to filter out just the numeric columns or just the columns with string values in them? Yes, it can, because I can use these in order to build another sub data frame. How do I do that? I use my df.select dtypes command, and then in the parentheses, I specify which data type I want to display, such as O for string values, int for integers, float64 for floating point values, and bool for Boolean. Those will show only true or false values. Let's take a look at that. All right. If I want to show just, let's say, the numeric columns in the adult data set, I will type df select dtypes and then int. So that should show me all the numeric columns. Let's see. Oh no, look at that. Here we have another error message. That tells me, and I'm jumping straight to the end, name df is not defined. Why is that? Well, because df really stands for data frame. And what is the name of my data frame? Adult. Oh, okay. So let's substitute adult for df and then see what happens. Okay. So whenever you see in a command language here, df always stands for the data frame that you're using in your notebook. So in our case here, it would be adult. In your case, it may be something else as well. So here, adult.select dtypes, you're seeing here, since I've chosen int, just the numeric values. If instead I use O to show all the string values, you're seeing all the columns with the string values. The string values themselves are not specific in many cases, but they are what we call categorical. Specifically sex, we have here in this data set only 2, male and female. We have here for native country, we have a number of them, but again, they're categories, right? We're seeing here there's a lot of United States here, there's Cuba here, and many more, of course, as well. Do data sets really look like this one in real life? We're seeing there's values in every column, there's values in every field. The answer to that question is really no. Data sets in real life are much dirtier. In many cases, there are missing values, right? And what good is a row with missing values to us, especially if that row causes us errors in the long run? In the context of a data set with 1 million, 2 million rows, really removing one row, removing 100 rows really doesn't have that much of an impact on the final results, but it will allow us to get our jobs done more easily. So how do you do that? You use the df.dropNA command and then set in place to true, which will help clean the rows with missing values from the data set. We already know that df will have to be substituted with the name of our data set. So here we can type adult dot and then drop NA, and then we will set this to in place equals to true, and then we will have removed any kind of rows in this data set that have values missing. You can even take this result here and put it in a new data frame with a df equals df.dropNA or adult equals adult.dropNA in place equals true, that kind of thing, in order to have a clean new data frame with which you can continue working. All right, let's shift gears to exploratory data analysis or basic statistics, which are the basic commands to give you an idea or a sense of what the data set is all about, how long it is, what the values are, numerically speaking, the largest, the smallest, what the averages are, or the middle number here, what the sum of the items is, and what the dispersion is with standard deviation and variance. In order to do this, we use our data frame name here adult dot, and then, for example, count. Here we're seeing that the count counts all the values in each attribute. So here we have a value in each attribute. We know that the data set is 32,561 rows long, and we see that there's a value in each attribute in each row. Now let's look at the minimum values. Adult.min. Here for age, the minimum value is 17. The smallest value in work class is a question mark. Same thing in occupation, same thing in native country. We'll talk about that later. For education, it's 10th. For education years, it's 1. And for relationship, it's husband. For race, it's American Indian Eskimo. For sex, it's female. For hours per week, it's 1. And for income USD, it is 20,002. Now these are the smallest values in each attribute, meaning either the smallest number or the smallest character or the character lowest in the alphabet that is being found. For example, here divorce starts with D. American Indian Eskimo starts with A, right? So how would you find the largest rows in each column? Well, in exactly the same way, right? Only that we use max. And you're seeing here the maximum age is 90. Work class here is without pay starting with W, right? Then education is some college starting with S, and so on and so on. Of course, you don't always want to look at all the attributes, and in a data set that has hundreds of columns, that might be slightly impractical. So you will want to look at specific attributes, right? So here you have the option of using the syntax data frame, attribute, and then whatever you're looking for, right? Such as the mean here for the adult age attribute in order to determine what is the average age of the person in our data set. So adult.age.mean gives us the result of 38.58. Now try this with the median, the sum of all the ages, and standard deviation. Oh, you know what? Let's do that. So here I would type adult dot, and then for the age, because that's what I want to look at, I type age, and then STD for standard deviation. And that gives me the standard deviation as the spread of the dispersion of the age attribute right here. Of course, you don't want to always use all of these commands, so there is an easier way to produce what's called this 5-number summary. And the 5-number summary happens with the describe command. So the syntax for this is dataframe.describe, and then whatever you want to include in your output. Here we're going to include all because we want to see all of our attributes in our output. That includes the numeric attributes, and it includes our string-based attributes. Now our output will be different based on these data types. Count shows us the count of values in these specific attributes or columns. Unique shows us the unique repeating values. Now for age, we're seeing there aren't any unique repeating values. Same thing for education years, for hours per week, and for income USD. But for work class, education, marital status, occupation, relationship, race, and sex, and native country, we have repeating values. These are our categories. So for work class, we have 9 categories. For education, we have 16 categories. That's 16 different possible values in this attribute. Marital status, we have 7, and so on. Top shows us the most frequently occurring, in this case, string in our column, such as private here is for working class, the most frequently occurring category, high school grad in education, and here we get the frequency with which this string occurs in our category. Then we're seeing mean, standard deviation, minimum, maximum, and then the percentiles 25, 50, and 75. Remember 50 is the median. Occurs and can be calculated for our numeric attributes. Now, we're not seeing this calculated for our string attributes because we can't do math with strings, right? But what if I want to see just my string attributes, for example? Then I can, instead of saying include equals all, I can say include equals, and then I'm going to use just my string attributes, namely the O. And that will show me just the string attributes. And you're seeing here, of course, the output is much smaller because I'm losing all the rows here with any numeric attributes. Attribute analysis. Same thing if I do this just for int, for my integers, I will see just the mathematical output and not the combined output here. All right, now let's take a quick look at how to group data by categories. You may have encountered group by in a database context. It's very similar here in Python. The group by operator uses the name of the attribute here in square brackets and in single quotes. But you're not seeing any output here because you haven't told Python what kind of output you want to see. You need to specify that. So here in this row, we are doing a group by on the race attribute, and what we want to see is the count of how often the attribute value appears in all the columns. So for example here, race, we're seeing that here. American Eskimo shows up 311 times. Asian Pacific Islander shows up 1039 times, and so has values in all of these columns. Now, we can also do this with the sum function here. For the sex attribute, we're seeing that we have 397,000 years combined age for all women, and 859,257 years of age combined for all men. The women, the females, have 108,095 years of education combined. Here's the combined education for the men, and then hours per week income USD. Now, for our purposes here, that kind of math may not make much sense. It will make much more sense if you split the group by for example, education years per sex, for example, and then look at the median at the 50th percentile. That way you can say, well, for 1 year of education, the median age for women is 39.5. For men, it is 42.0. Here is how many hours per week they work with 1 year of education. Here is how much money they make. And we're seeing that with increasing education years, here, if we look at the men make less than women here, but as we get to 10 years of education, we're seeing that at 10 years of education, men now make more than women. In fact, women with 10 years of education have a lower median income than women with 1 year of education. Now that's interesting. That would be an interesting data point to investigate why that is that way. Which raises the question, really, just because you can, should you, right? Does it really make sense to build a summary of everyone's age? Would you summarize your student ID numbers? Would you summarize zip codes, for example? Does that make sense? Sometimes it doesn't. And just because you know the code doesn't mean that you should apply it. Critical thinking is so very important to avoid doing too much work or the wrong kind of work. What can we learn, for example, if we have all the ages here summarized? Not very much. If we have all the education years summarized, we compare them maybe to the age. Yeah, we could potentially learn something from that. If we look at all the hours per week worked, potentially as well. But again, be careful with how you are applying your math. Just because you can, should you? The answer to that is no. Looking at numbers is great, but in order to really understand your data set, you will always want to also make a graphic representation. There is different ways of representing data graphically, as you may well know, but we really have low information graphs and we have high information graphs. Let's start with a high information graph. A high information graph is always a box plot. A box plot is basically your 5-number summary in graphical form. So the box includes the 25th percentile, the 50th percentile, which is the median, the 75th percentile, and then what's below the 25th percentile and what's above the 75th percentile. It also includes the outliers here, right? And includes the highest normal value, the lowest normal value. So very important that when you represent your box plot with, for example, adult.boxplot, the scale is based on the largest values. That shows you here with Income USD, we have some pretty big values up to 200,000. We do not have those high values with age, education years, or hours per week. So the scale does not work for these 3 attributes. In order to pull out the attributes, you can specify those inside of the parentheses here. So if I want to display just my age and my education years and compare those, I will type adult.boxplot and then just use age and education years. Note here always the angular brackets inside of the parentheses. And that gives you the age and the education years. Much better representation than up here, right? But what if I want to see how the age groups are spread out among certain types of education? Then I can use a categorical attribute on my x-axis, such as education here. We remember that education has 16 different categories, which is what we're seeing right here. And these 16 different categories are on my x-axis here. And then I can say, well, I'm going to take my column age and I'm going to split that out by the education category. So I'm grouping that. And we're seeing that people with a 10th grade education, for example, range from about 21 to 51 years. People with an 11th grade education are typically younger on both ends, but certainly a lot younger on the upper end here. And people with a 12th grade education are even less dispersed here in age range. So that's an option as well. This is the group by calculation of the group by command in picture form. If you prefer to have more control over the formatting of the plot, you have the option of using Fig and Axe in order to, for example, set the title. Here you're seeing the title is set to basic plot. That shows up here. If you decide to color the outliers and use different symbols here, you can use marker face color and marker in order to change the outlier symbols from just the basic dots here. Here we have set them to green and we have set the marker to a diamond, which is what you're seeing here. You also have the option of flipping the plot to the side here. And in order to do that, we're setting the vertical to false, so it becomes horizontal. And we are here setting the marker face color to red. That gives us the red, and the S here in marker gives us the square. A lower information graphic, but a more popular one, is your histogram, of course. Histograms are basically columns that represent data counts within certain categories. So the default for the hist command here is 10. So you'll get 10 columns for whatever attribute you are selecting to graph out here. If you want to adjust the number of columns that is being built to represent your data counts, then you're going to have to set the bins differently. So here, instead of the 10 column output, I'm setting a 20 column output. These columns in our case here are called bins. And then I am using my Y label in order to set a label here for my y-axis. I'm using my X label to set a label for my x-axis. I'm using my plt.title to set my title, and then I'm showing my plot, and that's what you're seeing here. You're seeing that there is a big difference in the graphical representation between having 20 columns versus 10 columns, and we're seeing that here the age categories behave very differently than what we're seeing here. We can also show all the numeric categories really easily if we don't specify the numeric attribute and we just type a .hist. Just a .hist will give us histograms, 10 column histograms for all the frequency distributions for all the numeric attributes. And lastly, we can try to also group our histograms in the same way in which we grouped our box plots above here, age by education. Here you're seeing the education, here you're seeing the age. Since histograms depict frequency counts, this is going to look a little bit different. So here we have in our lowest age group, here we have this frequency for 10th grade education and so on. And you can already see that this graph is a whole lot more confusing than the box plot that we're seeing up here. So that in our case, we might want to choose a box plot for a cleaner and for a more high information representation. So just because we can, should we build a histogram that is grouped? Sometimes it works. In our case here, it really isn't as effective as the box plot. Another popular way of showing data distribution is with a scatter plot. In a scatter plot, we relate the distribution of a numeric attribute to categories in a categorical attribute. This is what we've done before with age and education. This is what we're doing again with age and education. And you're seeing here in our plot the actual data points themselves, like the age of a person with a 12th grade education. Here's the highest age, right? And the highest age of a person with a 1st to 4th grade education on the lowest, and that kind of thing. So it is an even lower information graphic than our box plot that we're seeing here, because here in our box plot we have, of course, the box and we have the medians here. But it gives us a very quickly digestible visual representation of the distribution of our data points across these categories. So that is the advantage. Yeah, and then there's the problem of pie charts and dials. Very often managers love pie charts, they love dials because They're very quick to read. They're nice and colorful in many cases, and they supposedly show information. But the problem with that information is they're just counts per category. Dials display ordinal data and ordered counts per category from small to large, that kind of thing. But really, pie charts and dials are very, very low information. They are a bit more complicated to set up in Python, so we will defer on that topic because we are looking at using charts and graphics in order to help us understand our data better. For that, we are looking for higher information graphics such as, for example, box plots. And that concludes our walkthrough of our first module. Thank you.